it's fine.
It's good? Oh, great. Okay. Okay, so thanks again, and thanks to the organizers for the meeting, and I appreciate the opportunity to give a lecture in this conference. So in the first, say, third of my talk, I will be speaking about like a general Riemannian manifold, and I want to look at the Dirac operator and explain how you can write the expansion of the heat trace, small time asymptotic expansion. But the metric that I have in mind is this Bianchi-9 cosmological model, and I want to talk about the spectral action for this. So let me write what it looks like. So it's a cosmological model which describes the expansion of the universe, and it is homogeneous but anisotropic. So it is going to have three different functions, W1, W2, and W3, which describe the expansion of the universe in the different spatial directions. So, and also, for a technical reason, there is a conformal factor which just depends on time. So let me just use this mu cosmic time. And this f is a function of mu. And there will be three expansion factors which just depend on the time. So the matrix looks like this. So I will explain what these sigma i's are. So here I'm thinking about a compact manifold, so there will be like a compact interval for the time mu and times the three-dimensional sphere. So these sigma i's are left SU invariant one, SU2 invariant one forms on SU2, which is basically S3. Okay. So and they're supposed to satisfy these relations. D sigma 1 is sigma 2 H sigma 3, and then cyclically you can just okay. So yeah, I wish to write the spectral action for like the Dirac operator for this metric, and then study the spectral action. And then there's a parameterization of Bianchi-9. This is called the Bianchi-9 metric, but there's a parameterization for Bianchi-9 gravitational instantons, which is a family of metrics which have self-dual Weyl tensors, and they're Einstein metrics. And the parameterization is given in terms of theta functions, and at the end, the terms in the expansion of the spectral action are going to give rise to modular forms when we substitute these Wi's and F with the parameterization of the gravitational instantons. And this talk will be based on joint works with Wentao Fan and Matilde Marcoli. So for the moment, let me just assume that I have a compact Riemannian manifold. And let me assume a general even dimension. So let me look at the Dirac operator, which we need a spin bundle and a spin connection. Then using the metric, we have this identification, and with the Clifford action, we have the Dirac operator. Okay, so I guess if I pick some local coordinates, and in those local coordinates I write a theta up A local coframe, like an orthonormal coframe for the cotangent bundle, and look at a pre-dual theta sub A. So in local coordinates, I can have an expression for the Dirac operator, which is going to be sigma theta A nabla theta sub A. This is the spin connection. And in order to get the spin connection, one can write the Levi-Civita connection and figure out the one forms that describe the Levi-Civita connection using the metric compatibility and torsion freeness, and then lift it to the spin connection and get an explicit formula for the Dirac operator in some local coordinate that will look like sigma gamma A dx nu theta A omega BAC. And this gamma A, we can just pick any global matrices, gamma A, gamma B, that satisfy these conditions. Okay. And their size is the same as the rank of the spin bundle. So basically for this metric, there will be 4 by 4 matrices. Okay. So maybe I should squeeze this here. So basically, I'm going to be interested in this A0 of D squared So as t goes to 0, this operator approaches the identity on an infinite dimensional Hilbert space, and the trace blows up to infinity, but there is a control over how it goes to infinity. And if one can find the coefficients of these Zilli-DeWitt coefficients appearing in this small time asymptotic expansion, I'm sorry, this is t squared, then essentially one has a formula for the expansion of the action functional in noncommutative geometry, which is basically, so these are the eigenvalues of the Dirac operator with their multiplicities. So it is really hard to have any information about the eigenvalues, but the point is that when you let t go to 0, these larger eigenvalues play more, like they have more contributions to this summation. And there is some expansion, and in this expansion, one has local information. So there are some local functions that give us this expansion. And so this is the same as studying the expansion of this as lambda goes to infinity in terms of some local information. So as I said, in particular, when there is no any information about the eigenvalues, it is really hard to say anything about this summation. But there are a few methods that allow you to to figure out some formulas of this type for the coefficients of this expansion. So first, I want to explain the pseudo-differential calculus that allows one to have these local expressions. Okay. There we go. So the idea of using the pseudo-differential calculus and heat kernel method is that so we want to pass to the Fourier mode and use the Fourier transform to express this operator D in terms of its symbol, and then use the Cauchy integral formula to find an expression for e to the power minus td squared. And inside the Cauchy integral formula, we will just use the symbol of the operator D. So what I mean precisely is that, so in some local coordinates, the differential operator that we have is going to look like this. So I can take the component-wise Fourier transform of the spinor S written in some basis, dxc. And the symbol is going to be a matrix-valued function defined in the local coordinates over this. X is a coordinate on the manifold, and C is natural to be assumed to be coming from the cotangent fiber at point X. So This is B. So I'm basically rewriting the formula for the operator, the differential operator D, but I'm just replacing the symbol so that using the Fourier transform, we have a symbol representation of the operator. So we can do something similar for the D squared, and the symbol of D squared will have 3 parts. Each of them is going to be, so each pk is going to be homogeneous of order k with respect to xc. And so this is the inverse of the metric times the identity matrix. So it's going to be a diagonal matrix, the principal symbol of the operator. So the idea is then, as I said, in order to get information about the trace of e to the power minus t d squared, to use the Cauchy integral formula. So gamma should go around the eigenvalues of d squared. So the eigenvalues of d squared are non-negative numbers. And as soon as we have this, then we can approximate d squared minus lambda. D is like an elliptic operator, so in the algebra of pseudo-differential operators, modulo infinity smoothing operators, it has an inverse, which is called the parametrics. So let's try to find an inverse for d squared minus lambda. So it's natural to assume that this has so we want the symbol to have an expansion, and since d squared minus lambda is of order 2, so then it's natural to assume that the parametrics or the inverse is of order minus 2. So each rj is going to be homogeneous of order minus 2 minus j, in the sense that t squared lambda, it satisfies this homogeneity property. So the point is that this the principal part is invertible. So you can just find the formula for R0, and then from formula for R0 you can find the formula for R1, R2, and then recursively you can find all these RJs. But the computations are extremely heavy, like already in R4, R6, you cannot do it by hand and one has to use a computer. But theoretically, recursively, one can find all these RJs. So let me, and for the computation of this, like to say that R lambda composed with this, it's almost the identity, one has to use this complicated pseudo-differential calculus, which says that the symbol of the composition is going to be very complicated and it has integrals involved. But there is an asymptotic expansion for this, which is a very nice formula, and one can use it. So these are all multi-indices alpha. So it's great that there is a very nice formula for the expansion of the symbol of the composition of two pseudo-differential operators. And this is something that one can work with. So using this calculus, then one can start finding these RJs. And at the end, one finds that R0 is going to be say minus lambda 1 over this guy times the identity matrix. And for n bigger than or equal to 1, each Rn is minus dxc alpha Rj dx alpha pk times R0. So as I said, if we have R0, R1 up to Rn minus 1, then we can find Rn. And there are many, many terms in order to compute Rn for n equal to 4, 6, 8, and so on and so forth. But if you do this calculation, then this coefficient a to n that appears in that asymptotic expansion, so as I explained, it is the integral of some local a to n of x and d squared. So then you have a formula for a to n x d squared. So there is an integration over Rn, and there is an integration over this counter. You take the trace of this matrix R to n, x xc lambda, d lambda, d mxc. So it seems like we have an integral formula for these a to n's. But the point is that because of the structure that this trace of this matrix has, it is possible to use some complex analysis and some basic analysis tricks to work out these integrals and have an explicit formula in terms of x. And these local invariants of this geometry are computed. And the first term basically gives the volume, and the second term gives the Einstein-Hilbert action. Essentially, the scalar curvature will be there, and then the next terms are some like some topological terms, and and then the terms further down are first very complicated to compute, and second there are some up to the point is that up to A6 Gilkey has some formulas for these A to nx in general, and then up to A10 there are some other formulas in some works of Abramidi and his collaborators, and I have seen this type of formulas in some papers, but it's very difficult to compute them. And then after A10, like for A12, A14, I haven't seen any explicit formulas. So, but essentially using this recursive technique, one can, in theory, compute these terms. So let me explain what this, the trace of this, what it looks like. So the trace of Rn so by induction, one can prove that to some power g. Okay, so when you look at R0, R0 is just a diagonal matrix with this on the diagonal. So, and then this flips and goes into the denominator, and then different powers of this expression in the denominator appear. And when you use the Cauchy integral formula to these counter integrals, there are some complicated terms that appear. So there was a conjecture of Ali Shamseddin and Alan Kahn. In their paper, they studied the spectral action for the Robertson-Walker metric, which looks like this. So there is one expansion factor for this homogeneous and isotropic cosmological model. So this is one expansion factor, and then this is the round metric on the three-dimensional sphere. So they used the Feynman-Katz formula and the Euler-Maclaurin formula to compute the terms up to A10 of the spectral action. And what they observed was that in the expressions, there are some irrational coefficients that cancel each other. And at the end, like up to A10, the Zilli-DeWitt coefficients, this A2 and X, they are expressed in terms of this expansion factor and its derivatives, and some polynomials acting on A mu and its derivatives up to a certain order, and only rational coefficients remain there. So they made a conjecture that, for any n, A2n should have this property. So in a joint work with Masoud Kalkali and Asghar Korbanpour, we used this heat kernel method and proved their conjecture. We proved that for any Zilli-DeWitt coefficient for the Robertson-Walker metric, one will see only rational coefficients. And our idea was to work out some recursive formulas for these Rnj alphas. using these recursive formulas and some invariance properties that this metric has, we could prove this conjecture. Then last year with Wen-Tao Fan and Matilda Marcoli, we started looking at this Bianchi-9 metric. And because of this SU2 invariance of the one-formed sigma I, we could guess that hopefully there should be some rationality property for the spectral action of the Bianchi-9 metric also. And then we did some calculations, and then we saw that, the scalar curvature and the following term comes out to have only rational coefficients, and the irrational coefficients miraculously cancel each other. And we wanted to prove it in general terms in the expansion for the Bianchi-9 metric. And this idea of finding these recursive coefficients for these Rnj alphas seemed to not work, because that metric, from a technical point of view at least, is way more complicated, and these Rnj alphas were branching out in a complicated way. And this proof, which had worked for the Robertson-Walker metric, even for the Robertson-Walker metric, the proof has some computer reliance. So we were hoping to find some elegant proof that would have no computer reliance. And also, we wanted to have something that would prove the result for the Bianchi-9 metric. I don't. Well, these are the two examples that we have looked at. But I guess that if you remove this SU2 invariant condition from the one-form sigma I don't think that. I'm expecting that the rationality result will be violated, just because of the way the proof goes.
Even though in Gilkey you always find the rational.
No. Oh, okay.
Looking at the first formula.
So the point is that, so you have the time mu. So these are like general functions of mu, a mu or wi's, and then there are three other coordinates describing the parameterizing the sphere. So before doing the integration over the sphere, there are irrational coefficients. And after working out the integration with respect to the spherical coordinates, only rational coefficients remain there. In that sense, yes. It's a little bit more subtle. Okay. So, and it really depends on, like, in what coordinates you write the metric. You can write it in the spherical coordinates, or you can write it in the Hopf coordinates, which interacts with this one-form sigma in a better way. Okay.
The statement about the rationality versus irrationality depends, or you mean, or?
Sorry?
You mean it only depends before you do the integral?
Like before doing the integral, there is an integration that before doing the integration, you see irrational coefficients. But for these particular metrics, after doing the integrals, you see that the irrational coefficients cancel each other, and just only rational coefficients remain there. Mm-hmm.
They additively cancel, or they multiplicative?
What?
You mean there was coefficients that had like a 1 over pi, and then the integral produced a pi? Is that sort of cancellation, or is it that there were?
Oh, no, like additively, they additively cancel each other, right? Yeah. Mm-hmm. Okay, so in order to get, as I said, an elegant proof that would also hopefully work for the Bianchi-9 metric, we use the Wojcicki residue. So the point is that the Wojcicki residue is like a residue on the only trace functional on the algebra of pseudo-differential operators on a manifold, and it involves an integration over the cosphere bundle. So when you go over the cosphere bundle, this G mu nu, C nu is equal to 1. And these are exactly the complicated denominators that appear in this expression. And when you use the Wojcicki residue, you don't have to deal with these annoying terms basically in these expressions. And also using the Wojcicki residue, there is no need to deal with this lambda. So just denominators, we kill them very easily and then just get some polynomials, and then we just combine that with the SU2 invariance of these one forms, and then we have a rationality result for the Bianchi-9 metric. So let me briefly explain what the Wojcicki residue is. Yeah. Yeah, this expression is precisely equal to 1 over the co-sphere bundle. So just killing the terms that are annoying. So Wojcicki's non-commutative residue, which was discovered by Adler-Manin in a one-dimensional case and then extended by Wojcicki to the general manifolds. If you have a classical pseudo-differential operator with homogeneous terms of order d minus j, so this is the integral over the co-sphere bundle of the trace of the term that is homogeneous of order minus the dimension of the manifold. Actually, if you want a precise definition, it is the integral of a one density over the manifold. And this one density is defined by this. So at each cotangent fiber, you look at the volume form on the unit sphere, and you multiply this by the absolute value of dx1 up to dxm. And there is an alternative definition for the Wojcicki residue. So if you want to get the Wojcicki residue, you can pick any Laplacian delta and send p sigma to the residue at s equal to 0 of the trace of p sigma Laplacian to the power minus s. So we had to use these two definitions of the Wojcicki residue in this work, and we had to know precisely how they are related to each other. So it turns out that this is some constant. Because of the uniqueness of the trace on the algebra of pseudo-differential operators, there is a constant, and we worked out this constant, and it is equal to 2 to the power m plus 1 pi to the m. Sorry? The dimension of the manifold. Yeah, so any vector bundle that you have, you can just choose a Laplacian there, and then this constant is not going to depend on the rank of the vector bundle. And then this just relates this over the co-sphere bundle definition to the spectral definition of the Wojcicki residue. So then we use the Mellin transform. Actually, if one uses the Mellin transform and combine this with that asymptotic expansion for this part and break the integral from 0 to 1 and 1 to infinity, which gives you some holomorphic terms. This is standard to see that m over 2 minus 1. and in particular, residue at s equal to 1 of the trace of the Laplacian to the power minus s is of this form. And then you can play this with this and make a little shift and get this theorem. So D is the Dirac operator on a 4-dimensional manifold. Then for any non-negative even integer, we have, so if you want the 2 plus rth Zilli-DeWitt coefficient, you can do this integral. With an integration over the co-sphere bundle, but I should explain what this delta is. This delta is simply something that you get from d squared and the flat Laplacian on the torus. So basically what we wanted to do, we wanted to just make some shift so that we could really express each Zilli-DeWitt coefficient as the Wojcicki residue of something. So what this flat torus does is that it just shifts the dimension of the manifold and then puts this Wojcicki residue of this operator, which is the parametrics of this delta, in the right place. But the point is that this is a flat torus, so it is not going to bring in any new geometry except some volume. It doesn't have any curvature. So what it gives us is really the Zilli-DeWitt coefficient of this operator d squared, the Dirac operator squared. Okay, so perhaps there is no time to elaborate on this that much. But combining this result, actually I should explain that I think a long time ago there was an announcement by Kahn that the Einstein-Hilbert action can be written as the Wojcicki residue of a power of the Laplacian, and then there were papers written on this subject. So this extends that in the sense that any Zilli-DeWitt coefficient can be written as the Wojcicki residue of some Laplacian. And for the proof of this rationality result, it is very useful to use this residue. So now let me explain the rationality result. So for the Bianchi-9 metric, so each Zilli-DeWitt coefficient is going to be given by an expression like this. Or it's better to say the integral of the expression that I'm going to write with respect to time. And then you integrate over the time interval. So this Q2n, it's going to be a polynomial of several variables with only rational coefficients. So we have the expansion factors, WRs, and then their derivatives up to order 2n with respect to time. Okay, so yes, as I said, one has to use this trick to express each Zilli-DeWitt coefficient as the Wojcicki residue of some Laplacian, and then combine this. So when you do this, you just get some polynomials right away and nothing annoying in the denominators and so on, and then combine this with the invariance of these one forms, and the result follows. So then one thing is that one would be really curious about is that what is the role of these rational coefficients? For example, in number theory, these modular forms are very useful for solving some combinatorial and counting problems. And when you write their Fourier expansions, you see only rational coefficients. And these rational coefficients have an intimate connection to why modular forms are useful for solving some combinatorial and counting problems. Actually, it is not just combinatorial problems. Like in different areas of mathematical physics and differential geometry, modular forms have always been very useful. So the question is, if there is a connection between these rational coefficients that appear here and existence of some arithmetic structure, in particular some modular forms in the expansion. And let me explain that the answer is yes. Maybe. So a brief explanation about what a modular form is. So a modular form of weight 2k is a function from the upper half plane, the complex plane, to C, which satisfies this property. So we have the action of the SL2Z on the upper half plane, which is f of AZ plus B divided by CZ plus D. And we want to have this relation. These are basically some differential forms on the moduli of elliptic curves. So something like this would be called a modular form of weight 2k. So say modular form of weight 2k if it is holomorphic everywhere. And by everywhere, I mean including infinity. Okay, so the modular group PSL2Z or SL2Z has two generators. One is the translation that sends Z to Z plus 1. And the other one sends Z to minus 1 over Z. And these are the generators. So if something is a modular form, it should satisfy f of Z plus 1 equal to f of Z, and f of minus 1 over Z equal to Z to the power 2k f of Z. Okay, so using this relation, we will be dealing with this strip in the upper half plane here, and some Z here can be sent to Q equal to e to the power 2 pi I Z in the punctured disk. So equivalently, I can write the function f of q as a function defined over here. So let me write it f tilde of q. And being holomorphic at infinity, it means that this Laurent expansion does not have any negative exponents. Okay. So the great thing about the modular form is that they appear in different areas of mathematics and mathematical physics. And then once you know that you have a modular form, there are some algorithms for computing these modular forms in terms of some well-known modular forms named the Eisenstein series. So examples of modular forms, if you want something of weight 2k, it would be the Eisenstein series defined by this. So let me just do the summation over pairs of integers, excluding the 0. Or there is this modular discriminant, which is of weight 12. Which you can also write it as a linear combination of G4 and G6. So as you see, it has a simple 0 at infinity, which is equivalent to q being equal to 0. Okay. So So now let me just give the parameterization of the Bianchi-9 gravitational instantons. Actually, this was done in a series of papers. First, physicists thought that there should be some metrics of this type that have self-dual Weyl tensors and which are Einstein metrics. So when they wrote, it's in a paper of Todd, when they write, to be honest, this is like a series of papers, like Todd, Manin, Nigel Hitchin, Ukumara, some work of Alexei Kitaev. And at the end, there is a nice parameterization written in a paper by Bobik and Korotkin. So in the early papers, when they wrote the self-duality condition on the Weyl tensor for that metric, the equations reduced to some very well understood equations, namely Payne-Levis-6 equations. And then, if you conformally perturb the metric, the Weyl tensor is not going to change. So that's why they use a time-dependent conformal factor to see if they can, within this class, find a metric which is also Einstein. And that's how these Bianchi-9 gravitational instantons, they started to look for them. And then in these papers of, as I said, I named several people. Some solutions in terms of theta functions were given. And the work was continued until in a paper by Bobik and Korotkin, they just gave a very explicit parameterization of these instantons. So let me write this parameterization. So let's P, Q, Z be complex numbers. And mu is the time, but let me just thicken the time to the right half plane so that I mu will be in the upper half plane. So I need to introduce these theta functions with the characteristics, which are essentially, these are some modifications of the Jacobi theta function. So there is a summation over z. So the exponential so think of this as I times I mu plus 2 pi I m plus p times z plus q So when we don't write z, it means that we are setting z equal to 0. Okay. So using this, the definition of these theta functions, now I can explain the solutions to those WIs for the instantons. By the way, I was expecting the question like whether these metrics are Lorentzian or Euclidean. They're Euclidean, okay. I didn't say that at the beginning because, I didn't want to get kicked out. Okay. So do I have still like about 5 minutes? Or?
About 10 minutes.
10 minutes? Okay, thanks. Okay.
While you're on that, are the Lorentzian ones the ones that are called these, like, they exhibit this chaotic, are they the ones that...
I don't know. I don't know. Mm-hmm. Okay. So let me write the solutions. So there are two parameters, P and Q. So if you fix the parameter, you get a gravitational instanton. So it is minus I over 2, theta 3 I mu, theta 4 I mu, So W2 PQI mu. It has a similar formula, so let me just write a little bit. So it's like theta 2I mu, theta 4I mu, and there is a fraction here. Theta 3. Another fraction, which are not the same. And finally, for the conformal factor, is 2 over pi lambda. Lambda is the cosmological constant here. Okay, so we substituted these solutions into the Zilli-DeWitt coefficients that we computed for the Bianchi-9 metric for A0, A2, and A4. And we observed something that was quite striking, and later we proved that it holds for all Zilli-DeWitt coefficients. So I mu is in the upper half plane. So let's fix some parameter P and Q. We have a metric, and then we have the Zilli-DeWitt coefficient, and let's apply the generators of the modular group to this I mu. So this is what we observed. So for the Bianchi-9, okay, so it's like really for the Bianchi-9 metric. So the two nth Zilli-DeWitt coefficient corresponding to the metric at point P and Q. So if I apply the first generator of the modular group, this is going to behave like vector-valued modular forms, and it is going to act on the parameters also. So we get the one periodicity up to applying something to the parameters also. And so say minus 1 over I mu, it is equal to I mu squared. So it seems like we are dealing with a modular form of weight 2, which is bad news because there are no modular forms of weight 2 except if you allow for some poles. So we observed this for A0, A2, A4, and then we were wondering why this is happening, and then we were quite sure that this should really hold. So let me abbreviate Fan, Marcoli, and myself. So the reason for this happening is that these Dirac operators associated with the metric at PQ So we proved that these are isospectral, and using the fact that these operators are isospectral and playing with the heat expansion, we proved that this really holds for any n in the expansion. So then the question is, how can we relate these modular forms or vector-valued modular forms to some well-known modular forms, like the Eisenstein series and the modular discriminant that I just wrote down? So the point is that they have some periodicity property with respect to P and Q. So if you change P with P plus 1 or Q with Q plus 1, there is no change in these Zilli-DeWitt coefficients. So if you start with some rational P and Q, the points that you essentially get in the orbit, there are finitely many points. And by doing an averaging over these points, we get some ordinary modular forms, modular having some poles. Because these modular forms are going to be just modular functions, it's better to say, which are a weight 2. So they definitely have some poles. So after finding the poles and eliminating the poles, it is possible to write the result explicitly in terms of Eisenstein series and the modular discriminant. So there are two types of situations. So in one situation, when you look at the orbit, there is a point whose first coordinate is 0. And in that case, there are poles at infinity. And if there is no point of that type, then there is no pole at infinity. So for the Bianchi-Nine metric, for any n belonging to Z, so I look at this A to n of I mu. And let me just look at one example would be the orbit that we get from the pair of points, P being equal to 0 and Q equal to 1/3. So this belongs to the span of G14 I mu divided by the delta I mu. And this orbit has 24 points. So I will just finish in 30 seconds. And A to n of I mu for any n belongs to the span of, so as you see there is a pole at infinity, and in this case G6. So this Eisenstein series G4 has a pole at this point, sorry, it has a 0 at this point, rho equal to e to the power 2 pi I over 3. So there's a pole of order 4 at this point. And in this way we can explicitly write these modular forms in terms of the well-known Eisenstein series and the modular discriminant. So thanks, I stop here.
Before we call the questions, I make a comment. This theorem by Fan, Marcoli, and the author was proved actually in the last century.
Sorry?
This theorem was already known last century. It was proved by Barry Lee, Strada, and myself. And there's something of that in my book. And to understand it, to understand the result, it's necessary to go back like 230 years more. We are no longer in the 20th century. We are in the 18th century with Lagrange formula. As the speaker explained, you have to compute the trace of an inverse operator. Then you use the Lagrange formula for inverting a series. And this formula can be expressed in terms of residues. So instead of the residues, you write minus 60 residue, and that gives you the formula.
Oh, so not this theorem, right?
Eh?
Not this theorem.
Of course.
So you mean this theorem of A2 plus R equal to Wojcicki residue of something?
Yes, yes.
So you use this, do you use a flat torus?
You don't need a factorial. You can use a factorial.
Oh, so what we did, we used the flat torus. Yeah, but this result, this modular form is completely new because the parameterization is very recent. The work of Babik and Korotkin. So, yeah, but we just use the flat torus too.
Any other question?
I have a problem with the scales. If I have an expansion in terms of the Seeley-Dewitt terms, if I have it with a trace, I generate spectral action. I have d divided by scale.
Right.
And I have an expansion in terms of Seeley-Dewitt terms plus the moments of the cutoff function plus the powers of this cutoff scale.
Right.
Here the scale is hidden in this t, what you were calling time.
Right.
Okay, there is because you can reparameterize this.
So,
This t, I have a,
right, I think,
since I want to use this for renormalization in general, so I need to have a scale at which so A4, which is the usual zeta function residual or something,
right.
comes with dimensionless parameters, and it is the A4 Seeley-Dewitt.
I think the whole expansion is really dimensionless, right? Oh, okay, so you're saying that the constant term is A4.
Yes. A4 A4 is multiplied by
Lambda to the power 0.
Power 0.
Right.
So this is dimensionless.
Right.
And then every other term has a power of lambda.
That's right.
starting from
That's
the
right.
first one.
Yes. I think so.
Now,
Yeah.
in terms of residues,
Mhm.
if I take the zeta function, then I only get A4. But in order to get that's because the zeta function has no scale in it, and therefore I get A4 because I do the calculation. But, I should expect to get only A4 because this is dimensionless, the only dimensionless.
Well, in the expansion, this is the constant term, the term that doesn't have any t coefficient.
That's right.
So the trace of e to the power minus td squared.
That's right. Yeah. Exactly. So
And-
this is the one without the scale.
And if we write this, well, A4 essentially gives you the value of this, the meromorphic extension of this zeta function, but it is regular at 0. So A4 essentially gives that value at 0.
So but if you're doing renormalization, you need the scale because you want to know the renormalization. You need to know the scale. So the scale in general, in all these residues that you're saying, is hidden in this t parameter.
Yes.
That we have. Okay.
Right. Yeah, there's a bit.
This particular term is no longer a residue. The residues are the terms that come before.
Yeah, essentially it's a residue. It cancels with the residue. No. No, it really cancels with some residues, some poles of the gamma function. So essentially they are residues, and that's why they can be computed, I think. There's a cancellation. So gamma function doesn't have, it has some poles, but the pole starts from here at 0, minus 1, minus 2, minus 3. So some cancellation of some poles with the poles of the gamma function are the main reason why you have some values of these zeta functions. But essentially, I think the main reason why these coefficients or some values of this zeta function or their residues can be computed is that essentially there are some residues, which is a computable object, quantity.